again, if you see a 0, get on that, make it not a 0, and I will update the grade book as soon as I see it and get a chance to update it. For sure by eligibility. Okay, so we kind of pick off right where we left off with chapter 4, where essentially we found the protons, neutrons, and electrons, and we had a pretty good picture or a model. Where we leave off here is Rutherford. Rutherford had a great experiment because he shot those positive particles, those alpha particles, and he said, hey, all of the center has to be a positive charge, and the electrons are around it. That allowed us to build a really good picture. And now the question was, okay, well, we started this whole adventure off with knowing about electrons, but we don't know a whole lot about electrons. So what this does is it takes a look at, hey, how can we know about electrons? So again, protons, neutrons, hey, they're in the center, there's a positive charge, they account for most of the mass. The electrons, all we really know is, hey, they're negative and they're equal. In a neutral atom, they're equal to the number of protons we have. So the work really is concentrated all on the electrons. Actually, this is the entire chapter focusing on the electrons here. So, see some pencils still moving. This will, it kind of seems like it takes a real curve, but it's because all of this work was really done by the top physicist of the 1920s and 30s. So we'll try to keep everything as related to chemistry as possible. But any questions? Anybody still need it? You good? Okay, so moving on here. Here is our dilemma here, is this. So physics get involved, or physicists get involved, and they say, all right, well, if the electrons are around the atom and you have this huge, ginormous positive charge, why aren't the electrons attracted to that huge positive charge? So in other words, they're saying, hey, if you have a huge positive magnet and these little negative magnets are floating around, why aren't they attracted to the center? Something has to explain what is happening here. And we really don't answer that until sections 2 and 3, when we get into a new defined quantum model of the atom. But in chemistry, they notice, hey, there is significant difference in chemical behavior for atoms that are very close to one another. So we take, for example, chlorine, argon, and potassium, which are elements 17, 18, and 19 respectively. And these things behave very differently. So chlorine is a very reactive nonmetal that, when left in the air or when left naturally at room temperature, is going to be a gas. Argon's also a gas, but it is not reactive. And then potassium, that next element there, is very reactive solid metal. And so they're wondering, okay, we have a gas, one's reactive, one's not. We have a solid that is also reactive. Why is there such a difference in how these things interact? And I probably should have highlighted this. This is the first point where they're saying, all right, Rutherford, you gave us a good picture, but there's more to it than all of a sudden just we have these electrons and these nice rings around it. So this is the first question mark of, hey, electrons, these negative things, they have to do more, and we have to know more about these. Anybody have any questions? Do I still need these? Good. All right, so what we also knew was this, that each element and each compound for that matter, what they did is they had this unique emission spectrum. And what really happened was this. They excited, or better, they added energy to these elements. And when they added energy, they emitted a light. And that light was unique to each and every atom, or if they're looking at a compound, unique to that compound. So they emitted a unique light. We'll get into maybe today talking about how that unique light is specifically varied. But here's kind of our twist turn on this whole section. All right, atoms emit a light when they get energy added to it. Now we have to learn about light, in which we've already talked about a little bit in this class. So we will not rush through this, but kind of tie everything together here. So any questions on this? Does anybody still need it? All right, so we will get into light. And as you're doing that, I just kind of want to make a note so we can track what's happening. And you don't need to write that down. Let's just kind of help track us. Okay, where are we going with all this business here? So we add energy to atoms or compounds. They emit this unique light. Light in itself, they knew at this time, exhibits this wave-like behavior. So again, think waves as it moves up and down. That is how this light is moving. So now all of a sudden, okay, well, we can correlate movement and light. Somehow we have to have some interaction. So what we're doing now is we're trying to explain how electrons are moving, because we know waves move in that up and down pattern. How specifically do electrons move? Any questions? Anybody need this? Moving on. With this, we have to have some basic knowledge of how waves move. Again, wave, as we have that up and down motion, is going to have four unique parts or characteristics here. One is that wavelength. So if we measure from crest to crest or trough to trough, we can find out that wavelength. Two is that amplitude. How tall is that wave from that beginning? And I call that beginning the origin. What we can do with those things is we can figure out the frequency. So the frequency is important, and we're going to see this later on here, because it is going to be directly tied to how much energy something has. So now, again, I know this is big world here. Atoms give off a unique light. Every single light has a unique frequency. This means that that light can have a unique frequency, or every atom can have a unique frequency, which means it can have energy tied to it. So now we've done two major things. You may not know it. Is we have all of a sudden said, hey, electrons give off this light when they get excited or heated up, or energy is added to them. We know light moves in this wave-like characteristic. And now all of a sudden, we're going to be able to correlate energy to this. So this is, again, kind of mind-blowing what we're doing here. But it's all from the basis of, hey, when we heated up or when we added energy, these electrons or these atoms gave off light. And so this is why we take that deviation from straight chemistry. Okay, any questions on this? Anybody still need it? Good. Moving on. All right, so again, just some more things about light. Again, we talked about the amplitude. The height's going to play an impact, again, correlating directly to frequency, ultimately energy. So two things. One, light moves like wave. We can correlate that light to excited atoms. And then two, we are going to try to tie somehow energy jumps into that amplitude. Now, the third or the fourth thing that is important here is how fast this wave is moving. Again, it's moving in that up and down pattern, all at the same speed, which is the speed of light, or 3 times 10 to the 8th meters per second. And what we're really interested in here is finding out frequency, because frequency is somehow going to be tied to energy. Again, these are our big concepts. You have to remember that, I know 2 people won Nobel Prizes for this. I think 3 actually did. These dudes are really, really smart, and they knew a lot, and they were making some really tied together concepts. All right, so anybody still writing? We're going to do these problems here with our wavelength examples here. So our problem, our wave speed equation here is our speed of light times our wavelength. Excuse me. Our speed of light equals our wavelength times our frequency. So in our first problem here, we have the speed of light, which is always a constant, to be 3 times 10 to the 8th meters per second. The problem here, it says, hey, go find the wavelength of this wave that has a frequency of 3.44 times 10 to the 9th hertz. And if we plug this back into our problem here, we get 3 times 10 to the 8th meters per second equals the wavelength, or upside down y there, times 3.44 times 10 to the 9th hertz. Now, how do I get this stuff on the right-hand side by itself? Divide. Now, a key thing is a set of parentheses, because we have scientific notation. Don't let that ruin your problem there. And when you do this, again, whenever you see scientific notation, just go ahead and put that in parentheses. Did anyone calculate this?
8.7 times 10 to the negative second.
Perfect. And wavelength would be in what units?
Hertz.
Not hertz. Meters, right? Length would be in meters. And if you don't like scientific notation, this would be 0.087 meters, which that's a pretty big wavelength. And we're going to learn, okay, well, what's the point of wavelength here? Now, any questions on how to do a problem like this? Okay, I'm going to skip over example B because it's basically the same format. It's just solving for wavelength, and that way we can move on here. Questions? Does anybody need anything? Okay, so going a little bit further here. Most of the time when we think of light, we think of things that we can see. That is a very small sliver in this whole thing called electromagnetic radiation. Now, a couple things to consider here. Electromagnetic radiation in science is just going to be light. They're going to just say, hey, we're talking about light. We think of light when we talk everyday nature here of what I can see. The big thing out of this with the electromagnetic radiation is that as you go through this chart, and I'll blow it up here on the next slide, if I increase my wavelength, my energy decreases, and vice versa, or opposite there. If I decrease my wavelength, energy increases. So we've gotten kind of sidetracked here in notes, but now all of a sudden, this business about light, and again, think more broad picture about light, is that we can correlate energy to this business here. The key thing here with these last couple slides is that energy can be correlated to light. Questions? Anybody still need this? All right, so great, good picture. Obviously, it's not in color for you. Big takeaway here is that, hey, what we can see is a very small portion of light or electromagnetic radiation. Now, here comes another thing here is this. Okay, we know that light has we know that light has energy. Now we get to this fact here. Well, what they did, and this is again early 1900s, what they did is they said, all right, what happens when you heat something up? So, for example, who's ever turned on their oven if you have an electric oven and you saw that metal look like it get red? Okay, what's happening there is this. As heat's added, you have this thing called black body radiation. Essentially, there is heat shown as light, and they're trying to figure out why that is. Why does that change colors when it's heated up? At this point, they're saying, okay, now we got to tie something together. We know that light has energy, and we know that when we heat things up, like our oven, especially an electric oven, it gets this red hot. It changes colors because heat's added to it. They went a step further and they said, all right, this business about energy can be tied back to these things can make specific energy jumps. So now what they're doing is, hey, as we add energy, it changes colors. This is affecting our matter and ultimately affecting our energy. Now, the big question here, and here's where Einstein comes in, is that, hey, when some objects are heated, they only emit certain frequencies. Big picture for us, that means, hey, they only emit certain colors. Questions? Anybody need this? All right, so here we go with this. And this is Planck. So I didn't really mention this, but Planck, he was able to correlate, okay, exactly how much energy is gained or lost by that object. And what he found was, hey, it only worked in certain levels. So think of like a stair step. He said, hey, this object can only gain energy at this point, this point, and this point. They cannot have energy gains or losses in between those points. It has to be this exact defined value. And so what he's able to correlate here is that, hey, the frequency is going to be directly correlated to how much energy they have. He goes way mathematical beyond this class or anything you would have in high school here. He's able to do some crazy math, and he's able to say, all right, this constant is because, hey, energy can only jump up those stair levels. This is going to be ginormous in determining how and why an electron behaves the way it does. Questions? Am I need this? So here comes that second part to that slide we just saw. It said that electrons can be knocked off. Well, what that means is that electrons, thinking of this, they can jump levels. So think about getting hit in a sports game. When somebody hits you and they knock you down, you're probably rocked a few levels. And so, again, think about, hey, that dude or that lady had to have a lot of energy to hit me and knock me down. Why is it that sometimes when we shine light, it knocks these electrons off or bumps them to that next level? So what they did, here's the final piece to correlate all of this jazz together. They shined light on this metal surface. Some light, red light, that had a very low frequency could not eject these electrons. Some light, blue light in this particular example, could bump these electrons off. Ultimately, they are figuring out, okay, to go through these different levels and to emit this different light, we're going to have a certain amount of energy. This energy can help explain more about the electrons. Again, Einstein wins a Nobel Prize for this, so don't feel like if you feel lost in the sauce at this point. He was one of the top physicists of the time. Slides do get shorter, I promise. Anybody need this? Have any questions? Okay, so what happens here is this, the photoelectric effect. What it does is it explains this. Light moves like a wave. They already knew that. Hey, light had to move like a wave, that up and down this. And we know all this business about a wave can be mathematically calculated. But it also has to have some type of energy associated with it. It has to have that bumping power, that smacking power. to be able to explain what happened here, why this jazz is happening. What they do, or what Einstein does, is he says, hey, light is going to have these packets of energy called photons. So essentially, you have to have something as light's moving to be able to knock something off, to be able to knock something to that next level. What this is able to explain is, hey, as things get excited, as atoms get excited and they emit this light, we can actually calculate that energy. And now we have this energy associated with this, and we can track those energy jumps and changes. So the whole big summary of this is we are tracking the electron via how much energy is given off by it. What this means is now we're going to have a better idea specifically where those electrons are and how they behave. Okay, any questions on this? Anybody need it? Gotcha. Okay, so moving on here, using Planck's constant or Planck's equation here, we have this minimum amount of energy, or a photon has to have a minimum amount of energy to make this bumping happen. If they don't have that energy, we can't go to that next level. Think about it like a game on your phone. There's certain games, I don't know what they are, but you have to have certain points to get to that next level. Well, this is the same way here. Hey, you've got to have enough energy, enough points to bump up to that next level. And so what we're trying to do is we're trying to build a better picture of those bumps for those electrons, or those steps for electrons, where they can and can't go. And as long as everybody's okay, we will do the first example problem, because the second one's the same way. I don't want to break anybody's heart. All right, let's do this problem here, and we will get this over here. So energy equals Planck's constant times our frequency. The energy is something we're typically going to solve. So that first problem says, hey, go solve E for energy. Planck's constant, again, it is a constant because think of be 6.626 times 10 to the negative 34th joule seconds. And then our frequency is going to be shown in hertz or inverse seconds here. So we have 7.23 times 10 to the 14th. And that, again, is 1/7. Now, we plug this business all back into our equation. Key thing here, because we're dealing with some crazy numbers, go ahead and put them in parentheses. That way it makes your life easier. All right, what do we get for E? I have it. Bring it, you have
4.79 times 10 to the negative 19. That's 4.8.
There we go. Okay, so I'm not too concerned about this. Again, the whole thing is, hey, now we can track electron energy changes. Any questions? All right, let's knock these two slides out. That way we're done. I know they're kind of lengthy here, but here, these are probably the most important slides that we have for section 1. And that is this. Every single element, every single compound is going to have a unique atomic emission spectrum. What that means is each element or each compound is going to emit a certain light. We have all this business about light that we just talked about. All those guys that won Nobel Prizes that put all this together. We, in chemistry, we can take what color it is when it gets excited or has those energy jumps, and we can assign it kind of like our fingerprints are assigned to us specifically. So we can identify what is in there, and we can identify what is happening to those electrons as they move up and down. Now, here's our big correlation all to this energy business here. They are only going to get excited if they have enough energy. We see that exciting, or an element getting exciting, if they have that minimum energy. Questions? I may need this. All right, so last slide here is this, and we will do this Friday. That's why I wanted to drive on through here. We will do some flame tests, and each and every, in this case, a compound, will have a unique flame color and can be talked about a little bit more in depth and in detail with the next section of notes too as well with this business here. But essentially, when we see something lit up, it's because that element is releasing energy in the form of light. All of that fancy business that we've talked about can help explain why we see that unique light. Okay, I will check these tomorrow. Don't worry about them. In case you missed something, you can grab it from a friend. We will continue to drive on. These are the longest section of notes.